my next speaker is Mark Cunningham from Axial 3D, who is going to talk to us, give us a brief introduction into what is quantum computing. So this is a new field for us. I'm just going to hand it over to Mark.
Hello, everyone. So thank you for introducing me. Thank you for inviting me to talk. I'm really excited about today. So I appreciate that this topic is completely different to what everyone else has been talking about today. But what I'm really keen to do is to show what the future of the computing industry might look like in a lot closer than we think. So the title of today is Qiskit 101, An Introduction to Quantum Computing. And my name is Mark Cunningham. So about me, I'm an undergraduate physics with astrophysics student at Queen's University Belfast. I'm a placement year machine learning engineer at Axial 3D, about to return to my final year of physics. I'm a collaborator at Artificial Intelligence Northern Ireland, or AI&I for short. And more related to this topic today, I'm a Qiskit advocate at IBM Quantum. So I'm only 21 years old. This is the first conference I've ever spoken at, and I'm absolutely terrified, so please go easy on me. But hopefully you enjoy the topic today. So content summary of what I'm going to be talking about today. I'm going to be talking about what's classical computing, which is basically what we use day to day. What is quantum computing? Who are the big names in quantum at the minute? Who are the big competitors? What's happening in the world? And then close to my heart, what is Qiskit? And I'm going to show you a bit of example code on how to get involved and start learning. So what's classical computing? In classical computing, we use bits to store information. They are the smallest unit of information. They can be either a 0 or a 1, either or. 1 is on, 0 is off, sort of like electrical pulses. And we use logic gates on circuit boards to perform operations on a computer, and, not, or, XOR, etc., etc. We perform these logical operations using transistors, which are tiny, tiny pieces of hardware on a circuit board. So Moore's law is a law that states that the number of transistors in a dense integrated circuit will double about every 2 years. And we have kept on track with that up until the last few years. So this begs the question in what happens when circuits start to get really, really tiny, that the laws of classical mechanics start to break down and the ugly world of quantum physics starts to come into effect. And it begs the question in how can we use that to our advantage? So as we talk about circuit boards getting really small, a problem that can arise from that is a phenomenon called electron tunneling. So electrons are the charge carriers on our computers, and when an electron passes a barrier, it classically shouldn't be able to. This is known as electron tunneling. So an electron is basically a wave as well, and what happens is when it reaches a barrier, its probability function starts to taper off. And what that classically tells us is that it can't magically appear on the other side. But as we can see here, it doesn't taper off completely, and there's a wee bit of room here for an electron to basically magically appear at the other side, sort of like walking up to a door and magically appearing at the other side. So we can see here the classical computing reaches its limits at very small, dense circuits. So the limits is that when we reach that, our data sets increase in size massively, and we won't have the processing power to approach these problems either efficiently or effectively, because we literally can't get any smaller or fit any more computing power into a small space. And the bottom line is that you simply cannot model a world that obeys quantum physics using only classical computation. So this begs the question, what is quantum computing? This picture here is IBM's quantum computer. I believe, I'm not sure how many qubits it can store. And the actual quantum computer itself is just a little chip down here. All of this fancy stuff here is basically to keep it very, very cold. So what makes quantum computing different? We use quantum bits, or qubits for short, to store information. Similar to bits, they can be a 0 or a 1, but what makes it really special is that it can be a superposition between the two. It can be a combination of both. It can have many possible states at the one time. The only caveat is that when measured, a qubit collapses to either 0 or 1, and the probability depends on the qubit latitude. It can hold so much more information than a bit. So as you can see from this image here, you have either a 0 or a 1 for a classical bit, but in a qubit, there's so much information you can store. You can have either 0 or 1, or 0 plus 1 over the square root of 2. So how does this actually help? Why is superposition actually useful? So a good analogy is this idea of trying to escape a maze with four possible paths. If I am a classical computer, what I'm going to do is I'm going to walk to the end of a path. If it's a dead end, I'm going to walk back and I'm going to keep trying every single path until I get to the end. This obviously takes 4 steps, and if that's a lot of paths, that takes a lot of time on a classical computer. But a quantum computer can represent all of these combinations at the same time. So it can automatically detect what is the best route to take much faster. So with every additional qubit, the number of states you can represent doubles. So for 64 qubits, and then there's this massive number here, you can store roughly 1 million terabytes. And what really makes this special is that you can process all of them at exactly the same time, unlike a classical computer, which has to do it all individually. So a modern PC can calculate about 2 billion cycles per second, and to calculate through all of those possibilities, it would take 400 years of processing. So it's really interesting to see how quantum computing can be seen to be useful to us. So how do we make a qubit? What actually do we need to have? You need an object that can attain a state of quantum superposition between 2 states. So these are some examples of what you can have. You can have an atomic nucleus where the direction of the magnetic moment can point in different directions with respect to magnetic field. And the challenge there is in placing and addressing that single atom to store a specific value. You can have a trapped ion, which is basically you take an electron off an atom and turn it into an ion, and then you can use electromagnetic fields to suspend the ion in free space, firing lasers at it to change its state and to store different information and run different processes. And then finally, you can have a photon, which is basically a packet of light, and it can be in superposition in the direction that it is traveling or waving. And it can assemble quantum circuits by sending photons around a maze of optical fibers and mirrors. And a lot of different companies use all of these methods, and there's many more as well. And there's constant source of debate on which is better, and there's pros and cons to all of them. So potential uses of quantum computing. Why am I actually deciding to talk today to a large audience of tech people about quantum computing? The biggest, most commonly known potential appliance is that it can be used to create private keys for secure encrypted communication. A hacker wouldn't be able to copy the key due to quantum uncertainty. If they were to measure those qubits, it would collapse and give the wrong key. Also, pharmaceutical drugs can be discovered faster, as modeling molecules is a computationally heavy task. It is a quantum task because that's how molecules behave, and it makes much more sense to model a quantum state with a quantum computer. It will also allow us to perform analysis of huge data sets, such as weather forecasting. And my personal favorite as a machine learning engineer is the applications of quantum machine learning, which is in a whole new 2-hour talk of its own. And also for thinking of the maze problem, we can also imagine air traffic control and even normal traffic control in general. So where are we with quantum computing today? These are some of the competitors, or the big names at the minute. We have Google AI, and their framework is known as Cirque. We have Xanadu and Rigetti, which are 2 companies in Toronto, I believe. We have IBM. We recently just have AWS, who have jumped on the bandwagon. We have had D-Wave, which is a quantum computing company, and also Microsoft as well. And in this link here, on the quantum computing report, there's a huge list of all the different players in quantum computing today. So let's talk about Google. Cirque is usable in Python, and Google recently intertwined this with TensorFlow Quantum. TensorFlow, for anyone who's not aware, is basically their machine learning framework. And we can see here on the left about how they are integrating quantum circuits into a Keras sequential model. A few months ago, Google made headlines when they claimed to achieve quantum supremacy, or as I like to call it, quantum advantage, where basically they demonstrated with a 53-qubit computer to solve a task much quicker than a classical computer, which was a big milestone in that we should all take quantum computing seriously, effectively. How TensorFlow Quantum works is basically preparing a quantum data set, evaluate that model, you can sample it or average it or measure the qubits, and then you can evaluate a classical model to evaluate the cost function. Next up, we have Microsoft, and they have launched Azure Quantum. They have made their own quantum computing language called Q#, sort of similar to C#, and they work in partnership with Honeywell and another company called 1Qubit. I haven't played around with Q Sharp as much as I would like to. There's only so many hours in the day, but there really is a vibrant community in there, and I find it very, very interesting. And they have gone about it in that rather than just adding on a package to Python, they've actually made their own complete language, which I find very interesting. And then next up, we have Amazon. So the AWS partnered with Rigetti to use their hardware, and they just recently released Amazon Bracket on AWS. It is in beta at the minute, where you have to apply to be able to use it. I got denied, so I can't talk too much about it. But I think it's really, really interesting, as so many people today and yesterday or this week will be talking about AWS. And I think it's really, really interesting how they're breaking into the quantum computing market and will bring it to the forefront for so many companies that may not have considered using quantum computing before. And then finally, the one that I have the most knowledge in is Qiskit. So Qiskit is the Quantum Information Science Kit, and it is the quantum computing framework operated by IBM. So it stands for the Quantum Information Science Kit, and it is an open source framework for quantum computing, which means all of the code is on GitHub. It provides tools for creating and manipulating quantum programs and executing them on real quantum devices on the IBM Q Experience or on simulators on your local machine. It uses Python, so it's easy and accessible to get stuck into. And basically, what I find extremely interesting and very important, the theme of this week altogether is cloud computing. And for me, the future of quantum computing is cloud-based. You used to have to be in a real physics lab to be able to use a quantum computer, but now you're able to use it from your own living room on your laptop, which I think is absolutely incredible. Science fiction levels of incredible. So this is the IBM Q Experience. This is my little homepage. And basically, IBM offer, similar to Google Colab, where you can go in, you have access to all of these different quantum computers here with different amounts of qubits. And there you can see here that there's a queue to run jobs in each of them. And over here, you can open up your own IPython notebook or Jupyter notebook and just get stuck in. You don't have to worry about configuring anything on your machine. You can just start coding and learning. There's loads of tutorials, which I'll talk about later. But I think this is absolutely brilliant for allowing people to educate themselves on quantum computing. And the actual interface itself, I really love. So summary of Qiskit, there's 4 elements to it as such. There's Terra, which allows you to actually build quantum circuits. There's Aqua, which is the quantum algorithm library. There's Air, which is the backends, real quantum computers and configuring simulators on your machine. And then there's Ignis, which is error mitigation, because quantum computers at the minute make a lot of mistakes. My favorite quantum algorithm is something called Grover's algorithm. It is available in Qiskit Aqua, so you don't have to worry about the maths behind it. And basically, it is the fastest possible quantum algorithm for searching an unsorted database. And it has a big O value of the square root of n compared to a classical linear search, which is O to the n. And I think that's absolutely incredible. And it is really cool to me to see that it is a good example of how quantum computing can be useful already in the world. So time for live coding. I'm not going to do live coding. My dad came up with the idea of recording myself programming last night. And to me, that's as good as everyone's going to get. And I think it worked last night, so I'm hopeful. So this is the IBM Q Experience. And this is me getting stuck in. We just import Qiskit. We have a quantum register for playing with our qubits, a classical register for reading the qubits. We make our quantum circuit. We apply some logic gates. And this is a diagram of the circuit itself. We can run it on a simulator on our local machine, execute the circuit to make sure everything works okay, and then we can plot a histogram to see how the results of the qubits have turned out. Then, when we're confident that it's working, we can load our IBM Q account. We can actually pick a real quantum computer, and we can execute that job on a real quantum computer, and it's that quick. This is basically put onto a queue. As we can see here, the job's queued, and I think there was 3 queues. Yep, 2 or 3. And it's that simple. You can execute your circuit on a real quantum computer, and it took me less than 2 minutes to write the code, which I think is absolutely, again, science fiction levels of amazing. Just going to skip on through here. And compared to our previous results here, we only had 2 results, which is basically, I'm not going to go into the maths too much, but we had 0, 0, and 1, 1. And that's because our simulator on our machine is the idea of a perfect quantum computer. But a good analogy, I think, is, let's say I have an 8-qubit machine, And I like to imagine qubits as I'm an English teacher and I've brought loads of children in the library for a reading session. You might find, let's say they're all 8 years old. Let's say 4 of them sit down at their desks and they're quietly reading and they're really stuck into a book. You have one child who sits on the computer and just plays games. You have another child that just runs around the library talking. You have another one that looks out the window and sees something pretty and runs out the door. And you have another one that knocks over everything in the library. To me, that is a good analogy of qubits, where some of them can be performing their calculations, but other qubits can get actually distracted and they can start suffering from quantum noise, essentially. And this would cause us to get some false answers. So that is where Qiskit Ignis steps in, where we try to mitigate those errors as much as possible. But compared to the simulator, you can see here that there's 0, 0, 1, 1, which was our expected answers, and they're roughly 50-50, but there's some outliers here, and that is because of quantum noise. So day by day, these errors are, there's constant research into error mitigation, and day by day, you do see progress in mitigating those errors, but we still have a long way to go. So this is just some more example of Qiskit. This is simply how to make a circuit. Error allows you to run it on either a simulator or a machine, a real machine, and then Aqua is for actual algorithms, such as Grover's. So here are some resources to get stuck into Qiskit. The Qiskit team have worked really hard in creating the Qiskit textbook. It has everything. It is completely how I educated myself on Qiskit. There's brilliant tutorials there, start to finish. They talk you through everything. They explain the maths behind everything. They explain how to get set up on your own local machine. Also, we have a YouTube channel where we code with Qiskit and we explain all of the intricacies of it. And also here, which I think is absolutely amazing, we created Qiskit Blocks. It was an IBM developer that created this, and it has integrated with Qiskit to educate especially young children how to use quantum circuit gates in an intuitive way that makes it easy and fun to understand. And some of the puzzles on the game I think are absolutely brilliant. So if you go onto the Qiskit website, or even look up Qiskit Blocks, you'll see how to get set up. And I think we have a video on it on the YouTube channel as well. And you can see how to get yourself set up and really stuck into it. And I think it's a lot of fun. It's a good way to spend your day in lockdown. So one last recommendation I have is a website called the Quantum Computing Report. I'm sure a lot of people watching this week are thinking about how they are going to progress their companies to deal with the challenges of modern technology. And I think this is a great resource to see what other companies are doing to prepare themselves and the developments being made, what startups are starting to come onto the scene, what the trends are for people working in the field. And especially, at least in 2020, I think one of the huge areas that need to consider quantum computing is any company that works in cryptography. I honestly do believe that it's going to be in the very near future where cryptography is going to be completely turned on its head. And I think it's best to prepare yourself for that as much as possible. The website is brilliant. I use it for any news updates on quantum computing, and it's definitely something I think everyone should look at. Thank you for listening. I'm sorry if I spoke very quickly, and I appreciate that it is a very dense topic. If you have any questions, message me on Twitter or email me here. Thank you to all of Axial 3D for having me, or no, for allowing me to take time out of my day to be here. And thank you for Kinos for having me. And thank you to the Qiskit team for supporting me so much in making this presentation and actually educating me on Qiskit as well. So thank you. That's
okay. Mark, thank you very much for your presentation. There's a lot of love here on the feedback we're getting for you. One of the clearest explanations of quantum computing that Mark has come across. I'm of a certain age, so I enjoyed the air, wind, water, fire reference there, if anybody else missed that. And yes, again, the future of this is in cloud computing. It's been a long time since I have set foot inside the QUB physics department, and the idea of being able to do quantum computing on a laptop, from my sofa. That's just fascinating stuff. It's really futuristic, and yes, the implications for cryptography, potentially the end of cryptography, are seismic. So thank you so much for talking about that today.